Hello everyone, I'm Okan Özdemir and I'm a master degree student at Istanbul Technical University, Turkey. In this presentation, I'll be presenting my K-band frequency quadrupler design and its measurement results. First of all, I'll give a brief information about frequency multipliers, then I will give information about their usage in systems, then I will continue with the advantages of frequency multipliers. Secondly, I'll be presenting the proposed frequency multiplier and its design considerations. After that, I'll show the measurement results and we will discuss about those graphs. Finally, in the last section, I'll compare the proposed frequency quadrupler with other similar works. Let's start. The frequency generation is an important part of millimeter wave and microwave wireless communication systems. Voltage-controlled oscillators generate high-frequency signals directly by employing an oscillator tuned at the fundamental frequency. However, VCOs need high-quality varactors for their performance. Moreover, they are governed by constraints of including low output power, phase noise, jitter, stability, and high cost. Due to the high cost of developing low phase noise oscillators, frequency multipliers are often employed with local oscillators operating at lower frequencies for microwave and millimeter wave signal generation applications. In other words, frequency multipliers are another alternative method to generate high frequency signal with low phase noise. What is a frequency multiplier? In electronics, a frequency multiplier is an electronic device that generates an output signal, and that output frequency is a harmonic of its input frequency. Frequency multipliers consist of a nonlinear device such as diode and transistors, and that distorts the input signal and consequently generates harmonics of the input signal. If needed, bandpass filter is used to select the desired harmonic frequency, and it removes the unwanted fundamental and other harmonics from the output. As can be seen on the slide, frequency of the output signal is n times of the frequency of the input signal. In theory, it is possible to have every harmonic signal at the output, but due to the non-ideality of the real world, it's practical to use up to 5th harmonic at the output. I mean, it's not practical to have 6th harmonic and use it to drive another circuit. If you need the 6th harmonic, then you have to double the input frequency first, and you have to use a tripler to have 6th harmonic frequency of the input signal. Or you can use the 6th harmonic directly, but you have to consider the noise floor, and you probably use an amplifier and a bandpass filter to have 6th harmonic with appreciable power and harmonic rejection ratio. What are they used? Where are they used? Frequency multipliers are preferred in systems such as frequency sensors and communication systems. We said that it can be more economical to develop a lower frequency signal with lower power and less expensive devices, and then use a frequency multiplier chain to generate an output frequency in the microwave or millimeter wave region. As can be seen in the figure, a frequency multiplier is used to generate the LO signal in a receiver chain. Another example is given at figure B. A frequency multiplier is applied in a frequency synthesizer system to multiply the signal generated by the VCO. Why do we use them? What are their advantages? In high frequency applications, frequency multipliers have advantages on oscillators in terms of DC power consumption, phase noise degradation, circuit complexity, and cost. All practical oscillators inherently possess an amplitude limiting mechanism. Because amplitude fluctuations are usually greatly attenuated as a result, phase noise generally dominates in these systems. As can be seen in the figure, frequency quadrupler cascaded with a VCO starts to perform better than a VCO itself in terms of phase noise performance. This means although frequency multipliers generates a theoretical 20 times log n phase noise power increase, in practice they still offer better performance than a LO developed at the desired frequency. As the frequency increases, not only does the design and implementation of wideband low phase noise oscillator becomes difficult, but also the integration of PLS at the fundamental frequencies requires wideband frequency dividers, which means per scalar, circuits, which increases the system power and design complexity. This means oscillators can be challenging on power consumption and circuit design in high-frequency applications. Our design requirements was input signal was 5 dBm at 5 GHz, 20 GHz output signal is needed with above 1 dBm power, harmonic rejection ratios are above 20 dBc including the fifth harmonics, input return loss and output return loss are lower than minus 10 dB, low DC power consumption and low phase noise degradation. In this figure, the schematic of the proposed frequency quadrupler is given. The frequency quadrupler circuit is designed with packaged gallium arsenide FET CE3520K3, a low-cost, low-noise FET of California Eastern Lab, since it requires low DC power consumption and good high-frequency performance is available nonlinear model. RO 4350B laminate of Rogers Corporation is used in the design since it provides good high frequency performance. All devices that are used in the design are packaged surface mount devices and soldered on laminate which has 10 mils height and dielectric constant of 3.66 between 8 to 40 GHz frequency range. Input matching network is designed to satisfy the maximum power transfer condition at the input section, and it has a shunt and series transmission lines TL1 and TL2. Stability of the transistor is provided by R1, R2, R3 resistors and C1 capacitor. Values of these four elements are calculated and optimized to prevent oscillations up to 40 GHz while having minimum insertion loss. Biased networks consist of lambda over 4 transmission lines and radial stubs at relevant frequencies, and DC block capacitors C2 and C4 are implied at the input and output respectively. Output matching network is done to achieve maximum conversion gain while having sufficient output return loss, and it consists of a series and a shunt transmission line TL3 and TL4. Additionally, TL5 and TL6 open stubs, which have lengths of lambda over 4 at the fundamental frequency F0 and the second harmonic frequency 2F0, are implied to the circuit in order to reflect unwanted harmonics and the fundamental signal at the output. Since TL5 has 3 lambda over 4 length at the 3F0, third harmonic signal also reflects back from the output. Therefore, it's ensured that only the desired 4F0 is obtained at the output. Bypass capacitors are implied to the DC input in order to decouple power supply unit from the RF circuitry. Transistor is biased at the near class B operation point since class B topology is rich in harmonics and has low DC power consumption. The quadrupler has drain source voltage VDS of 1.8 volts and gate source voltage is minus 0.5 volts. It consumes only 6 milliamperes of DC current while there is no input power and 17 milliamperes of DC current while it is driven with 5 dBm. The produced frequency quadrupler is shown in figure at right. The quadrupler is 15 mm in width and 20 mm in height. Input and output of the circuit is soldered with 2.92 mm surface mount RF connectors which have working frequency up to 40 GHz. Measured output power versus output frequency for different input powers is shown in this figure. Output power has minimum value of 1 dBm at 90.7 to 20.3 GHz output frequency range when input power is 5 dBm. Output frequency with minimum conversion loss differs from each other for different input powers. As expected, minimum conversion loss at the center frequency is achieved for 5 dBm input power since input and output matching networks are optimized using large signal parameters of the transistor, which includes the nonlinear effects of the device for 5 dBm input power. Input and output return losses are plotted in this slide. Input return loss is lower than minus 10 dB and output return loss is below minus 20 dB at entire working frequency band for 5 dBm input power, and their minimum values are obtained close to the center frequency. Harmonic rejection ratio measurement results are shown in this figure. In the fundamental, the second, the third, the fifth, and the sixth harmonics respectively, 24 dB, 27 dB, 23 dB, 28 dB, and 22 dB unwanted harmonic rejection ratios are obtained. Minimum 20 dB harmonic rejection ratio is achieved for all unwanted harmonics and fundamental signal without any external filter. Finally, the phase noise measurements are done using UXA signal analyzer of Keysight Technologies. Since the input frequency is multiplied by the multiplying factor in frequency multipliers, phase noise increases by 20 log n 20 times log n in frequency multiplier circuits in theory. Based on this formula, phase noise is expected to have ideally degradation of minimum 12 dB in frequency quadrupler circuits. In this figure, M5 and M2 illustrates the input and output phase noise respectively at 0.1 kHz offset. M3 and M4 shows the input and output phase noise respectively at 1 kHz, and M5 and M6 illustrates the input and output phase noise respectively at 10 kHz offset frequencies. As can be seen from the phase noise measurement results given in this figure, the phase noise degradation is approximately 13 dB for 0.1 kHz, 1 kHz, and 10 kHz offset values. The performance comparison of the design frequency quadrupler with previous similar studies is summarized in this table. The design frequency quadrupler has high output power with low DC power consumption because of the selected topology and implemented matching circuits. In this table, it can be seen that good conversion loss with excellent phase noise degradation is obtained compared to the other works. Also, wide input power range with good harmonic rejection ratios are achieved compared with other proposed frequency quadruplers. Additionally, the frequency quadrupler proposed in this work is a cost-effective design. My presentation ends here. I hope everyone enjoyed my presentation. Thank you for listening to me.